Okay, thank you. Thanks to the organizers for inviting me. This is my first time at a strings meeting, and it's been very interesting. I was asked to talk about the weak gravity and swampland conjectures, and there's been more activity in the general topic of the swampland in recent years than I have time to talk about in an hour. So I'm going to stick pretty close to the weak gravity conjecture and the swampland distance conjecture, which are the topics I've worked on the most, mostly in collaboration with Ben Heidenreich and Tom Rodelius. But if you're interested in more of the swampland program, there are two sets of lecture notes or review articles in recent years that I would recommend you take a look at. Also, there are two closely related talks happening at this meeting. Timo Weigand's talk right after mine and Aaron Palte's talk tomorrow will cover similar topics. Okay, so what is the swampland program? We have a space of effective field theories that can be coupled to quantum gravity. It's a very large space of theories, and we think that most of the theories within that space cannot actually be completed into consistent theories of quantum gravity. So we expect that quantum gravity vacua are a relatively small subset of all effective field theories. There are some isolated vacua, maybe ADS or DS vacua. There are moduli spaces, continuous families of supersymmetric vacua. But there are also big swaths of the space of effective field theories that simply cannot be completed into consistent theories of quantum gravity. And these effective field theories, which are in the complement of the landscape, were named the Swampland by Kummer and Vafa. And the goal of the Swampland program is to suggest some criteria by which, if you have an effective field theory you're interested in, you can judge whether it's likely to be in the Swampland or whether it has a chance of being an honest quantum gravity theory in the landscape. Now, in the past several years, there have been many different Swampland conjectures that have been formulated. And so here's a somewhat subjective attempt to list some of them on two axes, one of which is how rigorous or how convincing is the argument? Is it really something that there's a clear reason to believe applies to all theories of quantum gravity? And the other axis is how predictive is the statement, which could be a statement about how predictive it is about the real world for phenomenology or for cosmology. It could also be a statement about how predictive it is about mathematics. Some of these conjectures have things to say about, for instance, the volumes of submanifolds of Calabi-Yau manifolds. And again, this is very subjective, but I would say that we have a few statements that are fairly convincing. And one that I will elaborate on in a few minutes is the idea that there are no global symmetries in theories of quantum gravity. It's quite convincing, but it's also pretty useless in terms of predictive power, because what it tells you is that you cannot have exact global symmetries, but it doesn't tell you how close you can get, whether you can have an approximate global symmetry that holds to very good approximation. And so a lot of the other statements that people have been thinking about in recent years, like the weak gravity conjecture or its variations, are attempts to kind of quantify the statement. How close can you get to having a global symmetry without running into conflict with quantum gravity? And those statements, because they're strictly stronger statements, they tend to have been proven less rigorously, but they also tend to be more useful and have more predictive power. And then there are statements that are extremely predictive, like the claim that we cannot live in a de Sitter universe, we must live in a quintessence universe. That would be a dramatic statement about cosmology that would have profound experimental consequences, but also, at least at this point, it's not very rigorous. So one of the goals of this program is for us to try to move in this direction. We would like to take these statements and figure out, are they really true? Or in the cases where there are statements that we really do believe to be true, can we formulate stronger versions of them that are more predictive and have more to say either about the real world or about mathematics? Okay, so my talk will be divided into three main parts. First, I'm going to summarize the weak gravity and swampland distance conjectures and some of their variations. In the second part of the talk, I will talk about some of the relationships between these conjectures and some of the kind of hints that we have of what might be deeper principles that underlie these and could explain why they're true. And in the final part of the talk, I'm going to try to say some things about how these ideas might be connected to phenomenology. And my own background is coming from the direction of particle phenomenology and cosmology. So one of my main interests in this area is to understand how far away are we from bridging this gap between statements about quantum gravity and things that have actual experimental consequences. Okay, so before I define the conjectures, let me just kind of give you a brief kind of view of how some of these ideas are related. A lot of the conjectures I'm going to discuss are linking three ideas. One of those ideas is weak coupling. Another idea is large distances in field space. These tend to be related in that weak couplings in quantum gravity arise when we have scalar fields that obtain large vacuum expectation values. A third idea is towers of particles. These are familiar from Kaluza-Klein theory or from string spectra, infinite families of particles. And we'll see that those particles often become light when we take these limits of weak coupling or large distance. So these three things are closely interrelated. And a lot of the potential connections to phenomenology come from the fact that if I have a tower of particles, they can run in loops, and they can drive scattering processes, for example, to strong coupling as I go to higher energy, because more and more of these particles are appearing. And so towers of particles tend to be associated with low ultraviolet cutoffs on the validity of my effective field theory, and that's something that's potentially very useful for phenomenology. So if I had to give you two kind of slogans for phenomenological lessons to draw from the Swampland program, the first is that low energy physics can potentially constrain ultraviolet scales if we were to measure an extremely weak gauge coupling in nature. Maybe, for instance, a massless B-L gauge boson, which, given current experimental constraints, would have to have a coupling smaller than 10 to the minus 24. I think it's unlikely we will discover such a thing in our universe, but if we did, these ideas would immediately tell us that our universe becomes strongly coupled well below the Planck scale. The other slogan I would give is that the idea of technical naturalness might not be the right one. So low energy effective field theorists often invoke very small couplings without necessarily explaining where they come from, and say that that's okay because quantum corrections are small. But what this tells is that anytime you see a very tiny coupling, it's usually going to come at some cost. It's going to pull down the ultraviolet scale and give you a smaller range of validity over which you can trust your field theory. Okay, so those are kind of the big picture. Now let's start talking about some of the specific conjectures. And the first is something that's been a folk theorem for a long time, that there are no global symmetries in theories of quantum gravity. One early place that this was articulated was a paper by Howard George I. Lawrence Hall and Mark Wise in 1981. They pointed out that the standard model has the nice property that things that we see as global symmetries in the world around us, like baryon number, could simply be accidental symmetries. They're good symmetries, not because they're fundamental symmetries of nature, but simply because there are no gauge invariant operators that violate them that have low dimension. And so from that, you might expect that a generic theory of quantum gravity is constrained by gauge redundancies, but not by global symmetries. And one very sharp version of this was explained by Banks and Dixon back in 1988, that in string worldsheet perturbation theory, if you have a global symmetry, if you have some conserved current, you can simply explicitly create a vertex operator that makes a gauge boson that gauges that current, and so you see that it was never really a global symmetry in the first place, it was always a gauge symmetry. Another reason to believe this is true in general is an argument about black hole physics. One place you can find this explained nicely is a paper by Banks and Seiberg from nearly 10 years ago. And the idea there is that if we have a continuous global symmetry in a theory of quantum gravity, we can take black holes and we can give them big global symmetry charge. Just throw in lots of things that carry charge, make a black hole as big as you like. But because it's a global symmetry, the black hole doesn't have some electric field outside that you can measure that tells you what its charge is. There's no hair associated with the symmetry. And as a result, Hawking radiation doesn't care about the symmetry. So in particular, when the black hole starts to evaporate, it doesn't preferentially lose its charge, as it would if it had gauge charge. It will emit particles, and some of them might be charged and some of them might not, but it has no reason to kind of have a net loss of charge. And so if I start with big black holes, they will slowly evaporate down to smaller size. At some point, the size becomes of order the cutoff, where I don't trust Hawking to tell me what happens anymore. But the point is that if I started with enough big black holes with big enough charges, I could create infinitely many different black hole states of any charge that I like that are at the size at which I stop trusting effective field theory. And so I run into a conflict with the covariant entropy bound. So these are pretty persuasive arguments that don't depend on particular details of a particular quantum gravity theory. The folklore has actually been much stronger than this, though. People have believed that even discrete symmetries, for example, are forbidden in theories of quantum gravity, and it's much harder to make a general argument about black holes for that. But recently, there has been a general argument that's been given that no global symmetries are allowed in quantum gravity in the asymptotically ADS context. And this came from work of Harlow and Aguri last year. And I'm not going to give you the argument in any detail, but essentially it's an argument that uses entanglement wedge reconstruction. And the key point of their argument is they carefully define what they mean by global symmetry, because if you define it too loosely, you will simply find that there are explicit counterexamples. But they seem a bit pathological. And what seems to save you from pathological counterexamples is defining a global symmetry to be something that can act within a local region. So there's this notion that they call splittability, which essentially says there are symmetry operators associated with a given region of space, that tell you about how the symmetry acts only within that region. Given this splittability assumption, you can take a symmetry operator and divide it into a product of operators over many subregions, and the HRT surfaces associated with these subregions only penetrate partly into the bulk, and you can argue that points deep in the bulk will just commute with everything. And so in that sense, it cannot be a symmetry that acts locally within the bulk theory. So that's a convincing argument that there are no global symmetries in any asymptotically ADS theory of quantum gravity. But again, saying that there are no global symmetries is not very useful because it doesn't tell us how close we can get to approximate symmetries. And that's what motivated the weak gravity conjecture, which was formulated by Arkani Hamed, Model, Nicholas, and Vafa back in 2006. So throughout some of my slides, you'll see AMNV, that's referring to this original paper on the weak gravity conjecture. And the conjecture that they formulated is that there must be some particle in the theory whose mass is less than its charge in Planck units. And to be specific about the coefficient here, what we mean is this particle is super extremal in the sense that its mass to charge ratio is smaller than that of a large extremal charged black hole. Now, one reason that you might like to invoke this is that if this is true, extremal black holes can shed their charge. A big extremal black hole can decay into a smaller subextremal black hole together with the super extremal particle. Now, it's hard to formulate a sharp contradiction of what goes wrong if this is not true. But at least if this is not true, then there are infinitely many stable extremal black holes. The reason it's called the weak gravity conjecture is there's a different way you can look at the conjecture, which is to say that if I take two of these particles whose mass to charge ratio is smaller than 1, and I put them far apart from each other, and the only forces in my theory are gravity and electromagnetism, the electromagnetic force will overwhelm the gravitational force, and these particles will repel each other. So you could also look at this as a repulsive force conjecture, a conjecture that there exists some particles for which the long-range force between them is repulsive. In a theory with massless scalars, because massless scalars can mediate attractive forces, these are actually different conjectures. And so throughout most of the talk, when I say the weak gravity conjecture, I really have in mind this version based on extremality, but this other version based on repulsive forces has also gotten some attention, starting with a paper by Palti a couple of years ago, then work of Liersch and Weigand last year, and more recently work that I did with Heidenreich and Rutilius. So these are independent conjectures, and there's actually substantial evidence that both of them are true in string theory examples. Now, the weak gravity conjecture, like the statement that there are no global symmetries, also turns out to be a bit too weak to actually be useful for phenomenology. And one reason is that it didn't tell us how big the charge was. It told us about the mass to charge ratio, but it didn't tell us that these were not enormous objects with big charge. And in particular, it turns out that black holes can satisfy the weak gravity conjecture. Now, you might think that sounds like a contradiction because we define the conjecture to be the opposite of the black hole extremality bound. But that's the black hole extremality bound that you read off for asymptotically large black holes, which are controlled by the two derivative action. And if I have a theory that has corrections, for example, 4 derivative terms, these actually modify the extremality bounded black holes. And so instead of only having black holes above this line where mass and charge are proportional, I will find black holes above some curve. And in principle, depending on the coefficients of these operators, this curve can either bend up or down. So either the black holes will have to be slightly heavier than they would have been in the two derivative theory, or they can be slightly lighter. But in the last few years, there have been several different arguments that have been given that various principles like unitarity and causality actually constrain these operator coefficients in the direction that black holes always move in the direction of being slightly lighter than they would have been. And in particular, then, you could say that the black holes themselves get corrections that allow them to obey the weak gravity conjecture. Now, most of these arguments involve various assumptions that are somewhat questionable. So I wouldn't say that this has been completely rigorously proven. In 4 dimensions, there's a paper to appear by Arkani Hamed and collaborators that I think gives a very convincing argument, but that's specific to 4 dimensions. Nonetheless, there are kind of enough different lines of evidence that invoke slightly different assumptions that I think it's very plausible that this is just true. So the minimal weak gravity conjecture is probably true. It's probably satisfied by big black holes. But for phenomenology, that's not a very useful statement because that's just telling us about tiny corrections to black holes, not about light particles that could actually appear in low energy experiments. So there have been a lot of efforts to make the weak gravity conjecture into a stronger statement. In the original paper, they already suggested a couple of ideas. Maybe the conjecture could be satisfied by the lightest charged particle. Maybe it could be satisfied by a particle of minimum charge. It turns out there are explicit counterexamples to both of those things in simple toroidal orbifolds. So some of those simplest strong forms are simply known to be false. However, there's a lot of evidence for a stronger form of the weak gravity conjecture that tells us there's some sort of ultraviolet cutoff, which is parametrically at the scale of the gauge coupling times M Planck. There's a squiggle here, so it's a little loose. There was one argument in the original paper for that, which was based on applying the conjecture to magnetic charges, saying that magnetic monopoles should exist with a mass that's below the extremality bound. And then if you interpret the size of a monopole as an ultraviolet cutoff, which is a reasonable thing to do for monopoles, because for monopoles, the classical radius is bigger than the Compton radius, so you really need some new understanding of what the physics is inside the classical radius. New degrees of freedom tend to appear there. If you interpret this as a UV cutoff, then you can derive that UV cutoff should be below the gauge coupling times M Planck. And that nicely fits with the idea that there are no global symmetries, because then if I try to create a global symmetry by making an increasingly weakly coupled gauge symmetry, in the limit when I make the coupling very weak and I have a very good approximate symmetry, I've also dragged my UV cutoff down to low scales, and my effective theory doesn't have much range of validity anymore. Okay, so that's the weak gravity conjecture and one of its stronger versions. The Swampland distance conjecture is another statement that was formulated by Uguri and Vafa back in 2006. And for a while, it wasn't getting as much attention as the weak gravity conjecture, but in the last couple of years, it's played a bigger role in the story. The idea of this conjecture is that string theory doesn't have fixed parameters. It has scalar fields whose vevs determine coupling constants. And in particular, there always seem to be limits within the moduli space where you can take these scalars to have very big values. There are limits that are infinite distance, and the effective field theory always seems to break down in those regions. And what Uguri and Vafa noticed is not only does it always break down, but it seems to break down in a particular way. There are always a tower of particles that exist in the theory that become lighter and lighter as you move further in one of these directions. And in particular, they become lighter in a fashion that's exponential in the distance in field space. So this is the distance you measure with whatever the kinetic term of your scalar field is. And I'll give you an explicit example in a minute. Another development from about 5 years ago was to formulate what the weak gravity conjecture should be in theories that have multiple gauge fields. And the idea is that if I have multiple gauge fields and I claim that there should be particles charged under each gauge group whose mass is less than their charge, that's a basis-dependent statement. We should seek some basis-independent statement, and one natural guess at what that right statement would be is that any extremal black hole should be able to discharge by emitting some charged particle. And it turns out that statement can be formulated geometrically. We can look at the space of charge to mass ratios of objects in the theory. And so black holes, again, will obey some extremality bound, which says they live in the interior of some region in this space. Extremal black holes would live on the boundary of this region. And no black holes, at least in the two derivative action, would exist outside this region. And then what the weak gravity conjecture should tell us is there should be some particles that exist outside the black hole region, such that the convex hull of their charge to mass ratios contains the black hole region. If that's true, then any black hole is able to decay into some combination of these particles. And if this condition fails, then there's particular directions in charge space where you can make black holes that have those charge to mass ratios, and they will be stable. They will not be able to shed their charge by decaying into these particles. So this condition for multiple gauge groups was formulated by Chung and Remen 5 years ago. And this condition led Heidenreich and Rudelius and me to a stronger conjecture through a thought experiment about testing whether the weak gravity conjecture is robust. So we could have a theory that obeys the weak gravity conjecture, and we could ask, can we deform this theory in some way in the infrared to get a different theory that no longer obeys the weak gravity conjecture? And one simple thing you can do with the theory is to compactify it. Particularly if we have a supersymmetric theory, we can compactify on a circle of any size, and with sufficient amount of supersymmetry, the size is a modulus, and so we have a family of theories that all came from the theory we started with. And these theories have an extra gauge group because they have the U1 Kaluza-Klein gauge group from the momentum around the circle. And we have particles in this theory that are the particles we started with in the original theory, plus all of their Kaluza-Klein modes, which have charge both in the original gauge groups and in the Kaluza-Klein direction. And so if we plot their charge to mass ratios, they look something like this. They kind of accumulate when you get very large Kaluza-Klein modes. They live up here. And if you obeyed the weak gravity conjecture originally with a large enough margin of error, then maybe all of these things can be sufficiently far outside the black hole region that they contain it. But as you vary the radius of the circle, you will always find that there's some radius at which this no longer works, and you get directions where there are stable black holes. So the weak gravity conjecture is not robust under dimensional reduction. The fact that it isn't robust, you could take it as evidence that it's just a bad conjecture, maybe it's wrong, but it might be that there's a stronger conjecture that is robust. And we were led to such a strong conjecture, which also fits very nicely with the idea of the Swampland distance conjecture, because in explicit examples of quantum gravity theories, these limits where we take a gauge coupling to be small are also infinite distance limits. And so if Aguri and Vafa were correct that every infinite distance limit is associated with a tower of particles becoming light, that's going to happen whenever you have a weak gauge coupling. And you might guess that something stronger happens, that not only does some tower of particles exist that becomes light, but that a tower of charged particles exists that becomes light. And not only that, but these charged particles become light in such a way that they obey the weak gravity conjecture. Okay, so that's a guess at some stronger conjecture, which is now called the tower weak gravity conjecture. This version of it was first formulated by Andriolo, Junghans, Noumi, and Xu. That there should be infinitely many charged particles of different charges, each of which obey the weak gravity bound that their mass is smaller than their charge in Planck units. What Ben and Tom and I formulated a couple years earlier was an even stronger statement, which is called the sublattice weak gravity conjecture, which says that there's some lattice of allowed charges, so charge is quantized, there's some lattice of allowed charges, and there should be some sublattice of that lattice of the same dimension as the full lattice, where for every site in that sublattice, you can find at least one charge particle that obeys the weak gravity bound that its mass is less than its charge, that it's super extremal. So sublattice is strictly stronger than tower, which is stronger than the original conjecture. And to give you an example that kind of embodies all of these different conjectures, let me just remind you about Kaluza-Klein theory. So if we have a theory of gravity and we dimensionally reduce on a circle, we get a new theory that has gravity in lower dimensions. It has a scalar field, the radion, that controls the size of the circle. And it has a gauge field from the graviton with one leg around the circle. And the action looks like this. If we canonically normalize the radion, it appears in front, we canonically normalize the radion and we go to Einstein frame, so it doesn't kinetically mix with the graviton. Then it appears in front of the gauge field, and it appears in this exponential manner. E to the some constant times the canonically normalized radion appears in front of the gauge field. Large radius is associated with small gauge coupling. So weak coupling is an infinite distance limit in the scalar field phi. We have a tower of Kaluza-Klein modes, infinitely many modes. Their mass is proportional to the gauge coupling. In fact, they saturate the weak gravity conjecture in a supersymmetric theory where this radion is a modulus. And the reason they saturate the bound is that there's a BPS bound in those cases. The radius is exponential in the canonically normalized radion field. So in particular, these masses are exponentially small in terms of the field space distance, which is what the Swampland distance conjecture says should happen. And not only that, but there's an ultraviolet cutoff. If the extra dimension is big, the true cutoff of the theory is the 5D Planck scale, which is well below the 4D Planck scale that we measure from Newton's constant at long distances in 4 dimensions. And in fact, it's exponentially small, again, as a function of the distance in field space. Okay, so this is a simple, familiar example that satisfies all of the different conjectures. And one way to think about these conjectures is they're sort of saying that all of quantum gravity is actually a lot like this simple example. So anytime you get a weak coupling, this set of things that happen will happen, even if your theory is much more complicated than a simple Kaluza-Klein theory. Okay, so those are the definitions of the conjectures. Now I want to talk a bit more about why they might be true. Are there some underlying principles that might explain these facts. And I'm going to just mention a few candidates. These are some hints. The first three are very closely related to each other. One is the idea that gauge theory is somehow emergent, that it's not fundamental, but it's emerging from some strongly coupled thing in the ultraviolet. The second is that there's some universal scale of strong coupling. So if we calculate scattering amplitudes of photons or gravitons, they're all going to become strongly coupled at the same energy scale. The third is that all global symmetries are badly broken at the quantum gravity scale. So we said there are no global symmetries in quantum gravity, but this is an attempt to make that statement stronger. They're badly broken. And the last thing, which is at least so far less closely related to these, is modular invariance, which is often a useful tool to prove these statements in different corners of the landscape. So let me start with emergence. This idea of emergence was brought into the story of the weak gravity conjecture by Harlow a few years ago through a thought experiment about the two-sided eternal ADS black hole. So we have two different boundaries, and holography tells us that the Hilbert space of the theory should just be a tensor product of two different CFT Hilbert spaces. So any operator in the theory should live in that tensor product, but he pointed out that there's something that appears not to, which is just a Wilson line that threads this wormhole and connects the two boundaries. So it doesn't appear to factor in the way that operators should. And his suggestion was that the reason is that these Wilson line operators are not really fundamental, and if you really want to understand how the factorization works, you need ultraviolet physics. And in particular, there should always be some charged particles on which we can end a Wilson line. And what we see is this unbroken Wilson line in the infrared is some kind of emergent artifact of things that actually end on the charged particles. And there was a nice kind of toy example of reviewing how the emergence of a gauge theory works in the context of the CPN sigma model that he discussed, from which he could derive an inequality that looks a lot like the weak gravity conjecture. So there's a hint that there's something about this emergence that might explain where the weak gravity conjecture comes from. This emergence fact is also related to the existence of strong coupling at some ultraviolet scale. In particular, there's an old idea which has been invoked often by Guia-Duvali in phenomenology, although it's a much older idea, that if you have a theory with many light weakly coupled degrees of freedom, this theory will have a low cutoff well below the Planck scale. And one way to think about that is just any scattering process can involve gravitons that couple to all of these different weakly coupled degrees of freedom. If you have enough things appearing in these loops, then at some point they're going to be important and your loop expansion is going to break down. And you can estimate that happens at some kind of quantum gravity cutoff scale, which goes like the Planck scale divided by a power of the number of degrees of freedom. For gauge theory, similar things happen. If you have many charged particles, they run in loops coupling to photons, and they produce some sort of Landau pole or strong coupling in the ultraviolet. What we noticed a couple of years ago is that if you have a tower of particles that saturates the weak gravity bound, something interesting happens, which is that these scales are the same. So we could have a set of particles, charge 1 with mass e times m Planck, charge 2 with twice that mass, charge 3 with 3 times that mass, and so on. If you just count the number of degrees of freedom up to some cutoff scale, you would estimate that that cutoff scale is bounded by a power of the gauge coupling, e to the 1/3 times the Planck scale, and the maximum charge in your tower would be like e to the minus 2/3. But if you repeat this kind of exercise with the gauge theory, you would say the gauge coupling is changing in the ultraviolet compared to the infrared by integrating out these things. We're counting each of them now proportional to their charge, and so we're going to sum up the set of charges and get something that goes like the cube of our biggest charge. And so we would estimate that this breaks down when q cubed is like 1 over e squared, but that's the same scale. So somehow these towers of particles induce strong coupling in the same place. If you don't like talking about off-shell amplitudes, off-shell two-point functions, you can actually repeat this kind of dimensional analysis with actual honest on-shell scattering amplitudes, and you'll reach the same conclusion. And in fact, you can repeat it for any gauge group. If I have a set of particles that saturate these lattice weak gravity conjecture type bounds, they will drive gauge theory and gravity to strong coupling at the same scale. And in fact, we can go even further. We can think about scalars. So suppose I have a scalar field, and when I move in the scalar field space, I have a tower of particles that become light as the as the Swampland distance conjecture tells us should happen. So there's a special point in scalar field space. Let me call it phi equals 0. It will turn out to be infinitely far away. But I'm just going to assume a generic kinetic term for phi, and then assume there's some set of particles whose masses are going to 0 when phi goes to 0. So that tells us how phi couples to these things. These are all going to run in loops and talk to phi. And we can ask what happens if we demand that these loops drive phi to strong coupling at the same energy that quantum gravity is driven to strong coupling by the large number of degrees of freedom. And if you do this estimate, you find that the kinetic term goes like 1 over phi squared. So for Aguri and Vafa, there was a conjecture that towers of particles become light exponentially fast. What we're seeing here is that that exponential can actually be explained by this idea of universal strong coupling. So if you demand that everything is driven to strong coupling at some scale, you have no choice but to have a kinetic term that has this logarithmic form in terms of the mass of the particles. And one interesting thing about this idea is you could also apply it to scalars that are compact, like axions, things that move in a circle. So I can't go infinitely far, and the Swampland distance conjecture doesn't obviously tell me anything bad happens if I have an axion with a very big field range. But if you demand that that axion is driven to strong coupling at the same scale, you find there must be particles in the theory whose mass is changing as the axion moves around field range bigger than m Planck. There must be particles whose mass is changing by amounts that are big compared to the cutoff. And so if this circle of ideas is correct, then you should be worried anytime someone tells you they have a theory, for instance, of inflation with super Planckian field traversals, that it might not actually be possible to do that within the context of a single effective field theory. Okay, and one other idea in this same circle of ideas is the idea that monodromy enters the story, and I'm not going to say a lot about this because I suspect that Aaron Palti will tell you more about it tomorrow, but there's work by Grimm, Palti, and Valenzuela where they tried to very explicitly understand what happens in type 2b Calabi-Yau complex structure moduli space. And what they argue is that there are these infinite distance points, there are singular points in the theory, there's a monodromy that rearranges the spectrum of states when you go around that singular point. And they argue that infinite distances in field space arise only when there's an infinite monodromy orbit. So when you have infinitely many different states that are kind of getting permuted as you go around the singular point. And so there are infinitely many BPS states of different charges. And in that way, this idea of the Swampland distance conjecture of having an infinite tower of states when you go infinitely far in field space is realized here. And you can think of the infinite distance as emerging from integrating out these states. Okay. One other idea that allows you to kind of derive some of these statements is that global symmetries could be badly broken at the quantum gravity cutoff. There's an interesting link between the existence of charged particles and global symmetries, which arises if we think not about ordinary global symmetries, but about higher form symmetries. So if I hand you a theory with a massless gauge field, but I tell you there are no particles that are charged under it, then that theory has a global symmetry, which is a one-form symmetry that acts on Wilson loops. In fact, it has global symmetries acting on both electric and magnetic loops. But let's just talk about the electric ones. So there's an identity that there's some symmetry operator, which is associated with the sphere that links the Wilson line, which acts on a Wilson line and produces a phase. And if the symmetry is an honest symmetry, this identity will hold. And in particular, the correlation functions of these symmetry operators are all topological. If we have charged particles, that's no longer true. This is no longer a symmetry, it's broken. But there's an interesting idea that Clay Cordova, Kantaro Omori, and Tom Rudelius had, which is to try to say, okay, we know the symmetry is broken by the existence of charged particles, but what does it mean for it to be badly broken? And so they try to actually quantify how badly is this broken by an explicit calculation. In particular, these operators are simple things. The symmetry operator is associated with an exponential of an integral of the current of the one-form symmetry, which is just star f over the sphere. And the Wilson line, of course, is just an exponential of the gauge field. So if you understand correlation functions of the gauge field with itself, you understand correlation functions of these operators. And what they have argued in a paper that will appear sometime this year is that you can actually just quantify what it means for this to be badly broken. Essentially what it means is the potential V of R outside a static charged source should deviate strongly from having a 1 over R behavior. And so that's related to just computing loops of all of the charged particles. And what they find is that having a single charged particle is not enough for the symmetry to be badly broken at the cutoff, but having a tower of particles is enough to badly break the symmetry. And in fact, their calculations end up looking very similar to the calculations I told you about a few moments ago of finding a universal strong coupling scale from this tower of things running in the loop. So a different way to understand these results that Ben and Tom and I had is to say that these global symmetries should not just be broken, but they should be badly broken at the cutoff. And the interesting thing about that, one interesting thing about that, is you can try to apply the same idea not just to ordinary gauge symmetries, but to, say, axion shift symmetries or magnetic symmetries. And so there might be a lot more mileage to get out of this way of thinking about the problem. And the final thing I wanted to mention about kind of general reasons why some of these statements seem to be true is modular invariance. In particular, we were able to prove in perturbative string theory that the sublattice weak gravity conjecture holds, and there was a similar paper by Montero, Xu, and Soler at the same time, but they were interpreting this as a statement about ADS3 CFT2 instead of about worldsheet CFTs. But the idea is just to use the old idea of spectral flow. So we have a partition function that has a chemical potential. It has simple modular properties. In particular, when you assume that charge is quantized, and you also work out how this transforms under S-duality, you get some identity that there's what's called a quasi-period. If you shift the chemical potential by a multiple of the modular parameter of the torus times an element of the dual charge lattice, you leave the spectrum invariant. And so there's some quantity, which is the dimension of an operator minus the square of its charge, which should be invariant, and that tells you that if you know about some state, for instance, the graviton, which has no charge, you will also learn about the existence of many other states that are related to it, like the red dots in this picture. You won't necessarily find a state for every site in the charge lattice because the shift here is related to the current algebra level. So if you have a non-minimal current algebra level, you skip some sites, but you still find a lattice of charged objects. And there are similar stories in the F-theory context that have been worked out by Lersch and Huygens, so you will probably hear more about that in Timo's talk after this. Okay, so there's some circle of ideas that seems to maybe explain why a lot of these phenomena that we see in theories of quantum gravity are often true and often correlated with each other. Now I want to talk about whether this has actual useful applications in the real world. And I want to start by giving you kind of an extreme example of a theory that phenomenologists are interested in because it's easiest to apply things to the most extreme cases. There's an idea that's heavily used in phenomenological model building, which is the idea of technical naturalness, which says it's okay to have a tiny number in your theory as long as that number is protected in some way, so when you compute loop corrections, it doesn't change by very much. Okay, so we don't worry too much that the electron is really light because corrections to the electron mass are proportional to the electron mass itself, and so it seems to be radiatively stable. One extreme version of this is a theory called the relaxion that Peter Graham, David Kaplan, and Sergei Regendrin formulated a few years ago, where they try to explain the electroweak hierarchy through cosmological dynamics. So they say there's some scalar field phi, it interacts with the Higgs boson, so as phi changes, the Higgs mass changes. And phi also talks to gluons in such a way that it gets a potential similar to the way an axion gets a potential, which is proportional to quark masses. And so what happens is if the Higgs has a positive mass, nothing happens. But when the Higgs becomes tachyonic, the quarks get a mass. The quark mass turns on a new part of the potential, which are these wiggles, and the field gets trapped at the bottom of one of the wiggles. It's a very clever idea. It's very different from any other solution to the hierarchy problem that anyone has ever proposed. But at least the minimal version of it requires that this field move something like 10 to the 20 times the Planck distance during cosmology, and that it kind of wind around the fundamental period of this axion 10 to the 30 times. So there's a very big number that was just put in by hand in the Lagrangian, and the reason it doesn't bother them is it's technically natural. It gets small corrections when you compute loops. But I think the lesson of the Swampland ideas is that it should bother you. You should be uncomfortable having a tiny number in your Lagrangian if you can't explain where it came from. And in particular, it will usually be associated with a low cutoff, with some tower of states that's becoming light. And in fact, you can find explicit effects like that when you try to construct something like this in the context of string theory, as McAllister and collaborators did a few years ago. Now, there may be modifications of this model. There are models where you don't rely on Hubble friction, you rely on particle production that have been developed by people like Anson Hook and Gustavo Marcus Tavares that might evade some of these bounds. But this is at least a case where the Swampland might make you uncomfortable with things that some community of phenomenologists were happy with. That's an extreme example. You might like to apply this to more familiar theories. And there's been a lot of attention to applying these conjectures to axions. Axions are useful for many things in phenomenology. They're useful for solving the strong CP problem. They're also useful to give us candidate models of inflation. And in fact, many of the best theories of axions come from gauge theories. So anytime I have a theory with some extra dimensions, I can potentially integrate some gauge field over a cycle in those extra dimensions to get a scalar field, which is compact in my low-dimensional theory. And one reason this is appealing is that it helps solve what's called the axion quality problem. So if you want to solve the strong CP problem, you need QCD instantons to dominate the axion potential, which means any other source of a potential should be much smaller. And that's actually very hard to do if you just try to get an axion as the phase of some field in your low-energy effective theory. It's much easier to do in this context because the gauge symmetry protects you, and the corrections are exponentially small because they're all coming from instanton effects where you wrap some kind of object around the cycle that you've integrated over. And so, for instance, closed string axions often give very nice models for phenomenological applications. But we're talking about gauge fields, and we're talking about corrections in the potential that come from wrapping charged objects, Euclidean charged objects, around these cycles. And because we're talking about gauge fields and charged objects, the weak gravity conjecture has something to say about it. And this was already pointed out in the original paper back in 2006, that if you just kind of naively dimensionally reduce what the weak gravity conjecture tells you in the higher dimensional theory, it tells you that you should have instantons whose action is bounded by the Planck scale divided by the axion decay constant, by the period of the field. And so for applications where you want that period to be large, of which inflation is an example, if you want this theory, which is called natural inflation, where your inflaton is some axion that gets a potential in much the way the QCD axion gets a potential from some kind of instantons, it turns out that to fit the data and to get a model of slow roll inflation, you need the axion decay constant to be big compared to the Planck scale. And so what they point out is then your instantons are typically small, and you should worry that your potential is not really under control. In the last 5 years, there's been a lot of activity both trying to evade this argument through cooking up more complicated models, thinking about various loopholes, and to strengthen the argument by kind of patching up those loopholes and figuring out stronger versions of the argument. And I'm not going to have time to explain any of that to you, but I'll just mention there are various models like inflation, KNP alignment, and clockwork, which is just kind of the iterated version of alignment. You kind of wind many times around different directions in field space. These are clever models, but at least some versions of the weak gravity conjecture seem to constrain them, and there's a large literature on that now. Instead of telling you more about that, and if you are curious about that, there was a talk by Gary Hsu at Strings a few years ago, so some of you may have heard that, or you could look up his talk. I want to talk about a different application, which is related to a thing that's often bothered me about quantum field theory and the standard model, which is that it's very hard to give an airtight argument for why we believe the photon is massless. So in quantum field theory, I can just add a mass to an abelian gauge boson and nothing bad happens. If I add a mass for gravitons or gluons, I can scatter the longitudinal modes and they become strongly coupled at some scale, and I sort of see that the theory needs more ingredients. But if I add a mass for the photon, nothing bad happens. The longitudinal mode is extremely weakly coupled if the mass is small. And so we can ask, is there a reason why quantum gravity would be unhappy if our photon actually turned out to have a mass of, say, 10 to the minus 24 electron volts, which is perfectly consistent with everything we know about our universe? And here's a sketch of an argument. You can view these masses as Stuckelberg masses. You can introduce a fictitious gauge symmetry where you're eating some real scalar. And you might think the difference between Stuckelberg and Higgs is in the Higgs mechanism, you have the Higgs boson, you have the radial mode that changes the mass. And the Stuckelberg mechanism, you just eat a real scalar. But it's actually more subtle than that, because in a supersymmetric theory, even in the Stuckelberg context, you will have a radial mode, because SUSY requires it to exist as a partner to the mode that was eaten. Stuckelberg masses show up all over the place in string theory, but when you look at the form they take, the reason they're different from the Higgs mechanism is you have kinetic terms that are non-standard. So you have some complex scalar field that shifts when you do a gauge transformation. And in particular, unlike the Higgs, where I could just go to the origin of field space and turn off the mass, In the Stuckelberg context, the origin is infinitely far away. To send the mass to 0, I have to send the scalar field infinitely far, logarithmically far away in field space. And so the Swampland distance conjecture should make you think that maybe something goes wrong when I try to have extremely light Stuckelberg masses. And in fact, if you just go searching for Stuckelberg masses in string theory, you find you can get small ones, but only when you have, say, really big internal dimensions and a very low cutoff. And so it could be that that's explained by weak gravity conjecture-like ideas, and one version of that story is to say we could dualize the Eaton scalar to a 2-form. We can rewrite the Stuckelberg mass as a BF term. And now we can apply the weak gravity conjecture to the B field and say the limit where I make the mass small by making this decay constant of the scalar f very small is the limit where I make the 2-form gauge field really weakly coupled. In that limit, I should have low tension strings. And the difference between these and strings I get in the Higgs mechanism, strings in the abelian Higgs model, is in the abelian Higgs model I have strings where in the core of the string the Higgs just goes to 0, and the string is really well described by semi-classical effective field theory. But here the core of the string is infinitely far away. It's really kind of probing the UV physics of the theory in ways that we don't understand. And in explicit examples in string theory where you look at Stuckelberg masses, these are really fundamental strings or D strings. There's some objects that know about the UV of the theory. They're not just objects in the low energy semi-classical theory. And so the limit when these are low tension is a limit where the theory is breaking down and the cutoff is becoming low. And given experimental bounds on the photon mass, this is actually one of the weaker bounds, but one of the kind of conceptually cleanest, which just comes from timing different frequencies arriving from fast radio bursts. Given these bounds, you could argue that weak gravity conjecture inequalities would suggest the quantum gravity cutoff of our universe is below 10 MeV. That's certainly not true because we've done experiments at much higher energies than that. And so that suggests that the photon in our universe really should be massless. There's a loophole in this argument, which is that I may have misidentified the quantization of the U1. Maybe the electron charge is not 1. Maybe in terms of the fundamental charge, it's 10 to the 14. And there's some hyper-millicharged Higgs boson that gives a mass to the photon. That's consistent with these weak gravity conjectures, but it's also suspicious because in string theory, we never find light particles of enormous charges. And so I think that's actually another interesting direction for thinking more about proving Swampland statements. I'm going to show just one slide about de Sitter. There's been a lot of talk in the last year about the idea that quantum gravity might not allow de Sitter space, and there might be some inequalities that tell us that potentials must be steep or have tachyons. I just want to suggest 3 possibilities for what's going on here. The first is that what's really happening here is just some restatement or refinement of the Dine-Seiberg problem. So we've known for a long time that kind of asymptotic parts of moduli space tend to have exponentially falling potentials, and it's really hard to construct a minimum there. And most of the evidence for these inequalities that's been cited is precisely in those kinds of asymptotic parts of moduli space. So it could be that this is a statement that holds in asymptotic regions of moduli space, but doesn't hold more generally. It could be that the reason this often holds is that this is a way to satisfy some other fundamental criterion. And one suggestion of that came from Tom Rudelius, who said maybe quantum gravity actually has a principle that eternal inflation is not allowed. And then if you obey these inequalities, that's enough to forbid eternal inflation, but it's not the only way to forbid eternal inflation. For instance, you could have metastable de Sitter vacua as long as they're not too metastable, as long as they decay fast enough. And so it might be that the evidence for this statement should actually be reinterpreted as evidence towards some other conjecture. Or maybe this statement is actually true. But if it's true, then there are many explicit examples of constructions within string theory that seem to violate this. And to me, at least, that would be a very surprising breakdown of effective field theory. But there's been a lot of attention to this. I have not personally worked on it. Tomorrow, Liam McAllister will give us an update on the status of de Sitter in string theory and maybe have more to say about this. Okay, in the last minute, let me just tell you a direction that I kind of would like to see more progress, which is that there are many different energy scales in nature, and we don't understand how they're related to each other. And let me remind you how ignorant we are. So we often show this picture of inflation, dark matter relics, electroweak phase transition, BBN, cosmic microwave background, all the way to development of galaxies. But it's worth keeping in mind that there's a big part of this plot for which we have no data. We have data about BBN, we have data about inflation, we have nothing in between. We don't know what energy inflation happened at. The Hubble scale during inflation is uncertain by 30-something orders of magnitude. And string theory suggests that our universe has lots of different interesting scales: a string scale, a Kaluza-Klein scale, a Hubble scale during inflation, a scale of SUSY breaking, some scale where the moduli are found. And we don't know what any of these are. I've kind of written down optimistic guesses where you might hope to get experimental signals for some of these, but we really don't know. And in the last year or so, there have been various swampland inequalities that have been suggested that would actually relate some of these scales. So for instance, there have been inequalities suggested that relate the Higgs VEV to the Hubble scale of our universe, or that relate the curvature of an ADS space to the Kaluza-Klein scale. Just in the last week, there have been 2 different papers that suggest that the string scale might be bounded in some way by the scale of inflation. I would say that at this point, none of these inequalities have substantial evidence behind them. But I think it's an interesting direction to go in, to ask, could there be inequalities that relate some of these unknown scales either to each other or to scales that we already know? And that would be very interesting. Okay, so since I'm out of time, let me just repeat that there's substantial evidence that something stronger than the weak gravity conjecture is probably true. It involves towers of particles and low cutoffs. But we're really still in search of rigorous arguments. And a lot of the statements that are most useful for phenomenology, like statements about potentials and de Sitter space, are controversial and difficult, and not a lot of progress has been made in that direction yet in terms of really trustworthy things. And I'll just leave you with this picture. We have lots of ideas, but we really want to be up here with statements that are both rigorous and predictive, and we're not there yet. Thanks.
So thank you very much for this very nice overview. Questions, please.
Your argument against the Stuckelberg mass for the photon invoked a symmetry that we have no evidence for. So why should we believe it? That is, you invoked supersymmetry.
I invoked supersymmetry as an example right. So I would say that in the context of supersymmetry, it's easy to understand why this radial mode exists. My suspicion is that this is actually just a general fact about quantum gravity, that just as gauge couplings in quantum gravity are always VEVs of moduli fields, whether you break SUSY or not, the value of the Stuckelberg mass is related to the VEV of some field. But I agree, this was not a rigorous argument. I think it's a suggestive argument. I think if you look at actual examples of Stuckelberg masses in string theory, they seem to be linked in some way to these scales that the weak gravity conjecture tells us about. But I'm not claiming to have given you a proof of anything.
Hi, I had a comment about the bound that relates the string scale to the Hubble scale during inflation.
Yeah.
So that bound is saying that the Hawking temperature during inflation is less than the Hagedorn temperature. So I think it's a bound that is probably obviously true in the sense that if the Hawking temperature was higher than the Hagedorn temperature, then you would have an unstable string vacuum during inflation.
Thanks.
Yes, Elias.
As far as I know, whenever we have Stuckelberg-like masses for gauge fields in string theory, they are always associated to anomalous U1s.
Mm-hmm.
And in field theory, this can be obtained in a limit where you have a Higgsing, a normal Higgsing of the U1 with some part of the fermionic partners getting mass, some very high mass, and leaving an anomalous spectrum in the infrared. Now, this somehow should be probably connected to the arguments you were giving without probably having to use supersymmetry.
Thanks. Yeah, I agree it would be really useful to understand that connection with anomalies better. I don't have anything clear to say about it at this point, but I agree that it's a good idea.
Are there more questions? Yes.
About your picture, you talked about pretty much every point, but to the left you have no Majorana neutrinos. Could you just say something about it?
Okay, I can say something very briefly. I showed something on this slide. So there was a suggestion of Aguri and Vafa that there are no stable non-supersymmetric ADS vacua. And several years earlier, Arkani Hamed and collaborators showed that if you just take the standard model Lagrangian and compactify and compute the effective potential, there is an ADS minimum that you would get just from our universe. And neutrinos are important there in that the Casimir potential from neutrinos running around the circle is important for balancing the cosmological constant and producing a stable minimum. And so Aguri and Vafa suggested that if you're sort of careful with these numbers, you would find that you get a non-SUSY ADS minimum when you have Majorana neutrinos, but not necessarily when you have Dirac neutrinos. And there's been further discussion of that by Ibanez and others. However, the Aguri-Vafa conjecture says that there are no stable non-SUSY ADS vacua. And so there's an important loophole in these arguments, which is that we don't know that the ADS vacuum you get by compactifying the standard model is stable. Certainly, I would not believe that our universe is stable. And most bubbles you could nucleate that would destroy our universe, there would be a cousin of that bubble that you could nucleate in the ADS compactification that would destroy that universe. So I would say that I don't find these arguments convincing at all because they have this loophole in them which depends on really the high energy physics of our universe, whether or not there is an instability. And so I don't see any way to prove that no such instability exists, because it's really a phenomenological question about our universe and about arbitrarily high energy scales in our universe. So it's an intriguing idea that quantum gravity could tell us something about whether neutrinos are Dirac or Majorana, but the particular arguments that have been given I find unconvincing.
More questions?
Yeah, a comment about non-SUSY ADS.
Mm-hmm.
I mean, we know that there are non-SUSY CFTs, right? So
that's right.
There will be non-SUSY ADS background.
I agree with you. I have asked Kamran what the sharp condition is that distinguishes. So what he wants to say is there are no non-SUSY ADS that are weakly curved. But of course, that's a quantitative question of how weakly curved. So the only sharp statement I can imagine that someone might be able to prove is that there are no infinite families of progressively weaker and weaker curvature. But again, that would be impossible to apply to the real world because we wouldn't know if we're part of such an infinite family.
Yeah, I agree with this condition on weak curvature. It may be true, but often people forget about this condition and they just say there are no stable non-supersymmetric ADS, and that's obviously wrong, right?
I agree, yeah.
Can you wait for the mic?
When you talked about the weak gravity conjecture, you use extremality bounds in flat space. I was wondering if you could comment on how much has been incorporated of using extremality bounds of black holes in space-time with cosmological constant. For example, in ADS, gravitational potential is stronger, so your extremality bound is nonlinear in the mass charge. The charge to mass ratio is different from flat space.
That's a good question. So you could wonder in ADS if you should be trying to apply bounds that come from looking at small black holes or at large black holes, and those could be very different from each other. There has been some activity on thinking about what the weak gravity conjecture might be in ADS and what its CFT translation might be. So for instance, there's one paper by Nakayama and Nomura that looks at some examples. And yeah, you have to be careful about how the ADS radius enters. So if you translate mass to dimension, they're kind of order one ambiguities depending on how the ADS radius would appear in that formula. So there are a lot of things to think about. One thing that I'm intrigued by is there's a link between weak gravity and cosmic censorship that Santos and Horowitz and collaborators have found. And they're really thinking about cosmic censorship violation in ADS spaces. And they have a quantitative condition that they can check, when you put in a scalar field that obeys some bound, you can show that you no longer violate cosmic censorship. And so in doing that, they've made a particular guess about what the right translation is to ADS. And they have some numerical evidence that at least associates their guess with some other independent phenomenon. So I think that's an interesting hint that there might be a definite sharp statement there.
Perhaps one final question? Yes.
Hey, I just wanted to make a comment. So you mentioned that there can be this connection between the completeness of the charge lattice and the existence of higher form symmetries. But that's not, the connection, I just wanted to point out the connection is not if and only if. So there are examples where you have a charge lattice that's not complete, but there are no one form symmetries. So that's something that's true in some examples, but it's not always true. So in general, the conjectures are independent.
Okay, thanks. I'd like to hear more details of that sometime later.
Okay.
All right, I think we should thank Matthew again.